Okay, welcome everybody. So today we're going to tie up some more loose ends on graphical models. So I hope that today we'll get through a fair amount of stuff. We just have to, because otherwise we are so out of sync with the curriculum. So yes, it'll be a little bit faster than the past 2-3 times. We just have to cover ground. Yeah, I'm sorry, so I need your full attention. I'll try to keep things reasonably straightforward. You need to ask me questions if something is not clear. Understood? Good. So I won't be asking you that many times today, do you understand this? You need to ask if you don't. Sorry. And by all means do. There's nothing wrong with asking if something's not clear. Okay, so remember we looked at directed graphical models, and the simplest one that you can kind of come up with is a chain. And a chain is basically just, I have, variable x0, x1, x2, x3, and so on. And, well, I could have something like the initial distribution of x0 is, 0 with 40% and 1 with 60% probability. Then I have this transition matrix, and basically what that matrix here means is that, if I'm in state 0, then with 20% probability I stay in state 0, and with 80% probability I go into state 1. And likewise, if I'm in state 1, this is what happens. So this matrix is stochastic. It's not necessarily doubly stochastic, but it's a stochastic matrix. In other words, the columns in this case sum up to 1, not necessarily the rows. So you can see that this first transition increases the chances quite dramatically that I'll end up in state 1. In state, well, for the next one, it kind of mixes a bit more evenly. And for the last one, it just flips things. Okay. And so I can, try working out what the probability is for x1. Now, the probability for x1 is just, p of x0 times p of x1 given x0. And I need to integrate out over the initial state. Okay? So I could also write this as pi1, which is, the probability distribution for x1, is given by, this transition matrix times the original state. So the reason why I write this as a matrix vector multiplier is because computers are really good at that, and also because people usually have a little bit less trouble reasoning about matrix products than anything else. So, okay, but an interesting thing's happening there. Now I can do the same thing for p of x2, right? That's, by base rule, p of x2 given x1 times p of x1. Now the latter is given by that, matrix vector product above. So I can chain things together, and I get first the transition matrix going from 1 into 2, then the matrix going from 0 into 1, and then the original state. And some papers might define this matrix as its transpose, so you might see some variant of that. Let's put some MATLAB code to that. So here's what you do, right? You define those 3 matrices, you define the vector, and that allows you to work out the final state. Does anybody have problems with that so far? Yep. Pi is the initial state. So little pi is, so pi 0 is basically, or in this case I called it x0 would be, just the distribution of the variables initially, x1 the next one. And pi is this transition matrix, right? This is pi. And I'm just calling it this way. Yeah. So now what simply happens is that in order to get the distribution over the third variable, I chain those 3 transitions together. This goes from 0 to 1, this from 1 to 2, this from 2 to 3, and voila, I have the distribution of x3. And yeah, it's a proper probability distribution, so everything works out fine. If you had 100 of those guys, you'd just multiply 100 matrices. Okay. Does that make sense? Cool. Because what you've just done is you've understood the most important part of dynamic programming. Namely, that if I have, what initially here, right, I mean, if you look at this expression up here on top, to get the distribution over the last state, I mean, you have to sum over x0, x1, and x2. If they're all binary variables, I'd have to sum over 8 different states. This sum grows exponentially. On the other hand, this product here, the work for that just grows linearly with the length. And you've just made the most important step, namely figured out how to turn something that otherwise naively would run in exponential time into something that runs in linear time. Isn't that awesome, right? And it didn't really look very scary. Who's done dynamic programming before? Nice. So what kind of dynamic programming did you do? Did you do shortest paths? Who did shortest paths? Right? Cool. What else did you do in dynamic programming?
Seam forming.
The what?
Seam forming.
Okay. 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 Well, okay, so if you've done MDPs, POMDPs, then this should be really easy for you. Okay, awesome. So this is like, that almost doesn't count. This is really advanced stuff, right? Okay, so now I can make things a little bit more fun. I can ask for, a second order chain. So this, by the way, the first thing that I wrote up here is a Markov chain of first order. First order because it only depends on the previous state. I could have a second order Markov chain, which is basically one that depends on the previous state and the state before that. Okay? And so in this case, well, I just have, arcs that go 1 back and 2 back. And this is the equation. Does somebody have an idea how to rewrite this as a first order Markov chain? Yep.
Use tuples.
Exactly. Perfect. So the idea is to use tuples. So rather than having, xi depending on, let's say, xi minus 1 and xi minus 2, I define new variable zi to be xi minus 1, and then I simply have zi depending on zi minus 1, and one of the dependencies is trivial because basically one of the variables just gets mapped to the other one before, right? Namely, this guy just gets shifted, and the other one I use for conditioning. So this makes life easy. What this importantly means is that there is no, in principle, difference in the expressive power that you get from a first or a second or third or fourth order Markov chain, assuming that I can do crazy things with my state space. So the state space in this case, of course, if I use those zi's, is, well, twice as large. Because if I have the xi's being binary variables and the xi minus 1's being binary variables, then I have 4 different outcomes. If the xi's were ternary variables, so 1, 2, 3, then I would have 9 different choices. So, question, if I have a Markov chain of order k, what is the size of the state space that I need to deal with? And I have binary variables. Is it 2 times k or is it 2 to the k? Okay, correct. It's 2 to the k. So this is a big caveat. The longer the history, the larger the state space, and it can grow exponentially. Now, on Monday, somebody asked this really nice question about, well, what about those, transition graphs? Those transition graphs are vehicles for having possibly a longer state space, but still cutting down on the possible, evolution history of what you need to actually take into account. So in many cases, having such a transition diagram is a necessary ingredient to make things work. So for a problem that we worked on a couple of years ago with basically Olympic athletes, swimmers in Australia, they wanted to know, their coach wanted to know whether the athletes were swimming or how they were swimming or getting into the water and whatever. They were basically rigged up with a old version of, well, what you could now buy as a Fitbit, right? So they would be rigged up with various accelerometer sensors, and they would swim with this. Now, to analyze exactly what they were doing, because they wanted to know which stroke, the segmentation and all that, that actually created a transition problem that was fairly largish. And solving that directly would have been very expensive. But there's a couple of obvious things that you can do. You know that if they are walking on the ground, they cannot be swimming in the next moment. They actually need to get into the pool first. Or, it doesn't make any sense to do a freestyle stroke and then run and then do another freestyle stroke. You need to get out of the pool first, stop, and then do other things. So by imposing this additional, what's sometimes called grammar also, on the transition process, that's what really made the implementation of the algorithm feasible in the first place. And it worked actually fairly well, so in the end it worked better than what the coach could do. Okay. So this is where Markov chains and then additional transition processes come in. Okay, so if you're at some point bored, search for that hashtag and you'll find a lot of cringeworthy stuff. Yeah, he's Australian. So now let's look at what happens in general, right? So we have this giant probability distribution, and what we're basically doing is we're summing over, p of x0, and the rest of the product only depends on the first term. So we have this. I define this to be, what I'm calling the left message, going from the left to the right. And I'm multiplying this by now p of x0, p of x1 given x0. So this is what we already did before anyway. I'm just recapping things. And you can then get something that's, now a message that I'm calling L1, which before that in the octave code I called pi1. And then I get the next guy here. And so you can see that you can basically peel off one term after the other and then sum over everything from start to finish. We've already seen this. Now the cool thing is you could also start the summation on the right hand side, where you sum over the last variable and the second last one and so on. And now for chains, if I have a directed graphical model, that doesn't actually buy me something, right? Because what happens is that it's normalized anyway. So summing over the last child that doesn't have anything else hanging off it, that probability has to be 1 anyway, right? So if I have, p of xn given xn minus 1, then summing over xn is 1. We know that. So therefore, doing all this fancy stuff here wouldn't have helped me very much. However, there are cases when my distribution is not normalized, where doing this actually helps. So let me give you an example. Okay, so here we are. Okay, sorry. Yep. So if you basically observe, let's say, some outcome of this last variable. So I have something like I observe y given xn. Then all of a sudden I have this chain xn, x1. And if I want to find out something like p of x1 given y, then I have to use Bayes' rule to get that. Because p of x1 given y is proportional to the sum over x2 up to xn of p of x1 up to xn and 1. Right? And now all of a sudden, this big reddish blob to the right hand side here is not normalized to 1 anymore, because now you have on the you have this very last dependence here, right, from this guy here. So basically you have P of y given xn times P of xn given xn minus 1. So this now becomes my left message, L of xn, Ln, and the sum over xn will become my message Ln minus 1 over xn minus 1. Okay. So, but it's the same algebra that we had before. So the only thing is that now, rather than multiplying with this transition matrix pi, we have to multiply with pi transposed. And we start from the right hand side. Don't worry, we'll go through that in a specific example. So here's a little bit what happens. So for the forward recursion, you basically have this, you start with a left message, initial message, that might be the initial distribution. You have a function that couples this variable with the next guy. You sum over the first one, you get the one for the next one, and you keep on moving on. So that's the forward pass of the forward-backward algebra. And for the backward recursion, you start with whatever is an appropriate message. So in this case, it might be just one. It might be P of y given xn, in this case here. And then you just sum things out. Now, what this gives me is also things like conditioning and marginalization. So what I can do is I can ask questions such as, what's the distribution of all the other random variables conditioned on observing a specific one? I can do that. Or I can ask things like, well, what's the distribution over that specific random variable xi? And that's just the left message times the right message, because you summed over everything to the right, you summed over everything to the left, so this is the only one left over. Or you can ask for, pairs of variables. So this is going to be very useful once we do hidden Markov models. So more generally, here's what happens. We have this forward message, goes from I minus 1 to I. And I'm writing it in this form because later on we won't only have simple chains, but we might have general graphs where things branch off and come back and do crazy stuff. And in this case, you actually need to define from where to where you're sending messages. So this is not going to be just on a simple linear chain anymore, but this is going to go over trees and do lots of fun stuff. And the same thing will come back once we do undirected graphical models. So it's exactly the same algebra, the same algorithm. It just operates on different objects, M and F. So actually, let's maybe go through that specific example. So let's say I want to figure out what I'm going to have for lunch, right? And we start off by assuming that, initially, I am ambivalent to whether I brown bag or whether, let's say I have lunch at Tazzadoro. And so on top of that, I have a transition matrix. And to make things really simple, I've assumed a stationary transition matrix, and it basically goes as follows. If I go to Tazzadoro, I quite like it, and I'm likely to come back there. So with only 10% chance, am I going to brown bag the next day? On the other hand, maybe my own cooking skills aren't so great, so only with 80% chance will I, brown bag the next day, and with 20% chance, I'll go to Tazzadoro. Right? So that's a transition matrix. And let's say we have a chain over 5 days. I know the initial distribution, and furthermore, I observe that on the last day, you went to Tazzadoro. Right? So I know that P of x5 equals Tazzadoro is 1. So then I can ask something like, what are the chances that you're brown bagging or going to Tazzadoro on day 3? So I know the initial conditions, I know the last observation. Now we want to get the guy in the middle. Okay? So here's the code. So you set up the transition matrix pi, same thing as before. And the only thing is I've picked a stationary case because I don't want to type in 5 different transition matrices for the pseudocode here. That's the only reason. Just lazy. So in doing so, we can get the left message. So L3 is pi times L1. Right? It's going from 1 to 2 and 2 to 3. This would be the probability distribution of being at Tazadoro at day 3 without observing anything else. Right? That's 58% that I'm brown bagging, and 58% that I'm at Tazadoro, and 41 that I'm brown bagging. Okay. Now let's set R5 to 1 and 0. So that's basically I observed that I went to Tazadoro on day 5. So now the right message is just, the right message is from 5 to 4 and then from 4 to 3. Right? So it's basically pi transposed times pi transposed times R5. Okay, that's our backward pass. Now at this point, I have, the left message over, what my prior distribution would be, and the unnormalized part from the right. So note that R3 does not sum up to 1. It doesn't have to. I need to renormalize it to make it work out. And so I have to pointwise multiply. So that's dot star, L3 dot star R3, divided by the suitable normalization. And lo and behold, I see that, well, now my chances of being at Tazadoro have gone up to 77.45%. So initially, not having observed anything, it would have been about 59%, and now it's 77%. So you can see how observing something at the end changed stuff. It's very, very simple code. Right. So any questions about that example? Once you understand this, everything else is really easy. Okay. Yep.
Why we use pi transpose?
Okay. Because I need to do the reasoning backwards, right? So that's why, I need to. Okay, so let's look at the forward step, right? So for the forward step, I have P of xi is P of xi given xi minus 1 times P of xi minus 1. Sum over xi minus 1. So that's basically pi AB times PB sum over B, if you will. So that's P sub A is that. So that's basically P is pi times pi is pi times pi minus 1. That's not raised to the power, it's just the index. Okay, that's for the forward pass. For the backwards pass, what I have is the unnormalized term, namely I get, well, P of xi given xi minus 1 times some right-hand message, so let's just call it R of xi, sum over xi, this is R I minus 1 of xi minus 1. Okay, now this is again the sum over B pi, now BA, right, times RB, this is RI minus 1A. Now this is of course nothing else but that transpose. So in other words, what we have is that pi transposed RI is Ri minus 1. That's why I have to transpose. Does that make sense? So, yeah, this is one of the places where you can screw up in your code. Be careful about it. So just think it through what needs to be summed over. Okay. Now we're going to make things a little bit more interesting. Let's use trees. Right? So assume that at some point, well, depending on whether I went a lot to Tazadora or whatever, I might meet somebody, and if I meet that person there, we discuss a paper, and then maybe we write the paper and interesting things happen. So basically something else branches off. So that would be x6, 7, and 8. And so how would we do things there? Well, let's just actually start from one end. So the left message would be, p of x naught, p of x1 given x naught, and I sum. Okay? And I can start summing from the right hand side. And yeah, okay. Obviously here in this case, if I don't observe anything, those right messages would be all trivial, but that's fine. Okay, so I keep on summing further. Now at x2, on the left hand side, I really don't know what to do. Because I'm stuck, I haven't received anything else. Now I keep on going through. And what you see is that now you've received, the right message R6 from x6. That's the one here. And in doing so, I can now work out what the left message has to be. And there's actually a typo in there. So I have L2. No, sorry, I have R2. Okay, sorry, this is okay. So I have R2 of x2. And then the message that goes out on the upper left, this guy here, this green arrow, now will depend on what the state of the lower right chain is and what I've received from the left. So basically, x3 is influenced by everything that came down here from the lower right and that came from the left. So once you get that, you can basically do graphical models. So and then I keep on going and I keep on summing. So this is probably the most difficult part of the class today. Let me go through it again. Any questions so far already? So okay.
So just to clarify, which nodes are we observing in this example, and which nodes are we trying to ascertain information about?
Okay, very good question. So the setting here is a little bit trivial in the sense that I didn't actually assume that I observed any evidence at let's say x8, but you might be observing evidence at all of those vertices. So this is just to explain the general mechanism of dynamic programming. Because yes, indeed, if I were to just not observe anything at x6, 7, and 8, I might as well just throw it away. Because they are children of x2, so I could just trivially integrate out. But I might have observed something such as, well, I might have seen where you were at x8. And so and if I then wanted to, compute any information about the distribution of x5, suppose I only observe x8, but I'm interested in the distribution over at x5, I need to sum over all the other variables but x5. And so therefore, you get those right-hand side messages coming in from x8 until they reach x2. And I can clearly do them without, involving any of the other variables. I can clearly take care of x0 and x1. And so x2 becomes this pivotal variable that integrates the information from 6 and 1 and then sends it over to 3. And, once you have that, then that's all the dependency that you really care about. So mechanically, what happens is you basically have in this, okay?
The last slide. So
Yep.
if I don't observe any
is just all 1. So basically I can cut it off. Then it doesn't matter. Yep.
So I'm not quite sure about the message here you mentioned,
Right.
So is it the same as some probability or?
Okay. So these messages may or may not be normalized probabilities. So in this case, for the forward pass, we got lucky and they are actually normalized probabilities. But they need not. They just are going to be numbers that are greater or equal than 0. You then need to invoke Bayes' rule at any specific point to get a proper probability distribution. Right. So in other words, if I want to get something like P of xi, then this is of course nothing else than, you know, summing over all the xj's with j not equal to I P of x, right? But in some cases I might not have that explicitly, because I might actually have that condition on some other y. So I might have this divided by the sum over all the variables xj P of all this stuff given y. And so what you get from that is, this is just simply Bayes' rule, right? So you might have only this expression here. And then this still allows you to compute xi given y. So for instance, the x's might be what is going on in my mind, what I'm saying. The y's is the audio signal that arrives at your ears. And what your brain is doing is it's basically solving a Markov model where it's using the auditory information and a lot of additional prior knowledge of, you know, the fact that I speak English rather than Klingon, and the fact that I'm talking about machine learning, and the fact that I have a German accent, to infer then what I'm saying. So your language model for me probably has gotten tuned a little bit to the way how I'm speaking, just over the course of all the past lectures. And your language model for me might be different from your language model for Banabash, because he has a slightly different accent, he has a slightly different vocabulary, but we both talk about machine learning and we both speak English, at least we try to. So this is all the things that are happening behind the scenes for this dynamic programming. And you might have noticed that sometimes when you listen to somebody, some words might not be clear initially, but only as they keep on talking more, things become clear. So in this case, your brain is effectively doing that backwards pass and using additional evidence to infer what you might have said. Okay. So here's the really, in a nutshell, summary of this. So we basically have the left message comes in. We have a message from 4 which comes in. We then have a function that depends on, you know, f2 and on x2 and x3. That's, for instance, you know, p of x3 given x2. We need to multiply that in sum over x2, and that's our message to x3. So what this really is aggregate all the incoming messages, multiply with, you know, how that variable is coupled with wherever you want to send things to, sum over the variable that you want to get rid of, and there's your outgoing message. Okay, we've done this. You can check that this does the same thing. And here's where you care about it, where you basically don't have access to the x's directly, but only to some variable z. And there we go. Basically, you have p of x and z is, you know, this entire nice model, and that does exactly what we have. So I cannot go into a lot of detail here just because we are a little bit short on time, but what I hope that at least you learned a little bit is Markov chains. They allow you to deal reasonably with sequential data. you can use a longer history by having a higher order chain, but you can rewrite it again. And dynamic programming is basically just, you know, looking at your dependency structure and peeling off variables one by one until you have the term that you want. And this is great if the context is small enough, but it's really expensive if you have a very long history. So, now junction trees, I'll just tell you what they are, because there's just not a lot of time. And that's essentially a generalization of what happens if you don't have just a simple chain or a tree. Basically think of this as, well, a tree with highways. So in other words, where you have more than one variable that may show up in a vertex. And so in that case, adjacent vertices, the messages that you need to send depend on the variables that they share. And, okay, so same thing here. So here's an example of what happens. Let's say I have variables that depend like so on each other. Then I can write them as cliques, as in maximal cliques. And if I do this, then I get a clique tree. And the algebra works out exactly the same, except that now rather than simple trees, you have junction trees. And now instead of, you know, a single state variable, you have variables that might depend on several observations. So here it's 2, 4, and 5. So this is exactly the same construction as what we did before with the reducing a second order Markov chain to first order Markov chain. And the algebra looks exactly the same, but we don't really have time. The only caution is in many cases, if you do this, you might not actually end up with a tree, but you might end up with just a general clique graph. And this is not good because, so basically two edges are connected if the two cliques share a variable. And then the question is, you know, how can we turn this into a tree? And one is by simply, you know, adding some variables to it. So I basically go from, I basically change this into something that has 3 variables each. And that will give me now a chain. And that will then allow me to do dynamic programming again. But my separator set increases, so before that I had only 1 variable, now I have 2. That's obviously not the only thing that you can do. I can do something like this. Yep.
Why do you lose the directions when you form them?
So why did I lose the directions? Very good question. So first of all, there are graphical models that don't have directions. So they basically just model correlations as opposed to causal dependencies. They're called, very unsurprisingly, undirected graphical models. Okay. The dynamic programming that I'm going through here is identical for directed and undirected ones. So therefore, you know, once you've actually written out, you know, the functional dependency structure, it doesn't really matter, you know, what went into this. Furthermore, as soon as I actually observe certain things, you know, the random variables, a lot of the distributions are not normalized anymore anyway, so all the benefits from the directed graphical models where, you know, so I mean, yes, of course, if you have an unobserved random variable and nothing depends on it, you just get rid of it, sure. You do the obvious things. At that point, you're stuck with some core part where the probabilities are not properly normalized anymore. At this point, it's just pure algebra, and you just have to sum over variables where the directions in the graph came from. At that point, doesn't matter so much. This is why I threw the arrows away. On top of that, it's just faster to draw. Okay. And you get the very same thing here. You basically just now have more variables. So, yep. And this is just to give you an idea that this doesn't always quite do something very useful. If you have like a 2 or 3D grid, if you try to build a junction tree there, you'll go mad because this will just clump everything together into one big fat hairball. And that's the reason why doing graphical models inference in things like these things, so for instance spin glasses, is really hard. It's one of the reasons why, for instance, image denoising is really hard if you attack it naively. The fact that our cameras can do it suggests that they are efficient algorithms, and that would be a really cool class in its own right. So basically what I've shown you a little bit is that you can go beyond just simple chains, and yeah, sorry, there's not enough time. Now, one thing that you need to know though is the generalized distributive law. Because I've been talking about dynamic programming, and it looked nothing like the things that you've done before, right? Because you probably did something like a shortest path calculation, where you go from A to B, and you probably may have heard about the Viterbi algorithm, but then what I showed you was algebra that looked so different, right? Now, the really cool insight, this is something that happened about maybe 10, 15 years ago, as in this was when the papers that formally explained that came out, is to realize that actually all those algorithms do the very same thing. They just do different things when they talk about addition and multiplication. So there's something called a semi-ring, and a semi-ring is basically a mathematical object where multiplication and addition is defined, and where the usual, distributive properties hold for, addition and multiplication. So in other words, A times B plus C is AB plus AC, and on top of that, A plus B plus C is A plus B plus C. And this holds for, of course, multiplication, but it also holds for all those things. It holds for max and plus, and it holds for set, union, and intersection. It holds for ands and ors, it holds for log plus and plus, and it holds for the min and plus. Okay. So who's seen this kind of stuff before? Okay. So what I suggest is that pick one of those 6 items. Well, maybe not the first one, because for that one I hope that you know that the associated and distributive law holds. But pick one of the other 5 and check that under the right definition of what plus and times means. So for the second line, for instance, plus becomes max and times becomes plus. That in that case, the distributive law and the associative law still hold. Actually, let's just prove it for the second one. So I need to prove that A plus B plus C equals, and I'm just putting that circle around, which just means it's a general version of a plus, A plus B plus C. And I know that plus means max, and times means plus. Okay, so now we need to show that the maximum over A and the maximum over B and C equals the maximum over A and B and the maximum applied here. Okay. I guess everybody knows that this is true, so I don't need to prove it any further than it's already. Okay, so we've just checked associativity. To check distributivity, I need to check that A times B plus C equals A times B plus A times and the usual rules of, you know, precedence of operators hold. Okay, so I need to therefore check that A plus, here we have the max of B and C equals, okay, A plus B. Now the plus is a max, so we have the max here, and A plus C. And I guess that's again self-evident that this is true. And you know, you can do this for the other 4 cases there. Now that looks kind of bizarre, but it means that any algorithm before where we had, you know, plus and times, you just redefine plus and times to mean max and plus, and immediately you have the shortest path algorithm. So before that, you know, remember max, so plus becomes max, so we have the max over, so this is basically the most likely path through that graphical model. That's, you know, what you want to do if you want to, for instance, build a parser. And that's now the max over, you know, the first variable plus then, you know, whatever depends on the second one. So again, you have the same left message, and you just work your way through. So it's exactly the same algorithm, just that now plus and times you have max and plus. Any questions here so far? The really cool thing is that you can, for instance, implement that in Python, just as, you know, class with, you know, corresponding addition and multiplication. And then by just swapping out the different semi-rings, you get immediately efficient implementations for very different algorithms. So a student of mine did that at some point, and this was like a 10-line Sudoku solver that you get out of it. It's quite fun. Okay. Any more questions? Okay. So for cliques, same thing as before. Now the last thing is, of course, you're not really allowed to have any loops whatsoever in this case. So before that, I showed you already that, you know, you can, how you turn those loops. That would give you, you know, not a junction tree, but a junction graph into a graph by just adding edges. But quite often people just do that anyway. And this is called loopy belief propagation. And in very large graphs, this is not the most horrible thing to do. And there is some theoretical argument why, under certain circumstances, the outcomes are not quite as disastrous as they would appear. But you would really need to take a graphical models class. But just as a heads up, while I'm telling you that you shouldn't be doing this, your cell phone is probably actually doing that very thing by using turbo codes. So turbo codes use exactly that idea. Okay. And of course, you can fix things, but that's a different story. So now after all this theory, let's switch gears and let's look at clustering. Okay. And sorry, this was fairly fast, but we just need to cover ground. Okay. So who's ever used clustering before? Awesome. Who of you used k-means? Okay. Did you ever wonder why k-means is doing something sensible? Well, maybe. Right. So here's what is happening. So let's do density estimation, right? We've done this before. This was, for instance, what we used in exponential families. So we have, you know, some xi's that we observe, and we have some latent parameter theta, and then, well, that's just fine. Now, if we have just a single Gaussian and the data looks like it comes from a single Gaussian, that's good. But in many cases, that's not quite the case. Because you actually might have objects that are much more similar to each other and reasonably well concentrated, And quite often this is how scientific discovery works. So if, for instance, you look at, you know, breast cancer treatment or whatever, initially they treated everybody the same, and then they found out there's like 10 different subtypes, and then for each subtype you find a different treatment, and somebody else comes along and says, no, there's by the way a subtype, and then there's by the way something else. So by actually inferring all this structure, you can really save lives. Or you can make a lot more money if you do that on the internet for showing ads, right? Those are useful things. So, in other words, in many cases, a simple model may not really fit the data very well. So here's one option. And it's just for mixture of Gaussians, but you could have mixture of whatever else. So you might basically have, you know, some means and covariances. Right? And, you know, they look like so. They may overlap, they may do interesting things with each other, right? And those means and covariances are where my data might come from. And then I have some variable y, which is like a switch variable. And I first decide, okay, I'm going to pick maybe cluster 2 today. Let's just number it, 1, 2, 3, 4. And then I draw a point from cluster 2. Next time I draw maybe from cluster 1, pick a point, maybe here. And I keep on doing this. Maybe again cluster 2, then cluster 4, and so on and so on. And this, of course, will give me a distribution that is now considerably more interesting than just a simple Gaussian, yet it's made out of very simple components, just simple Gaussians. So the nice thing is that I can, through that, do something that's very complicated, that looks very complicated, yet actually has fairly simplistic ingredients. And yeah, that's the graphical model for it. Well, actually, I lied to you. This is really what the graphical model is. I need to have a prior on the means and covariances, and I need to have a prior on the probabilities. By the way, implementing this model with a sample is going to be one of your assignments. Okay, so might help to listen. So here's the joint probability distribution, right? So conditioned on, you know, all the means and covariances, what I have is that basically, you know, the joint distribution over the data that I'm observing, x, and the y's, which are the cluster memberships that I'm not observing, is just, you know, p of x given y sigma and mu. So this is really easy. That's just a standard Gaussian model. And then the distribution over the cluster memberships. Does anybody have questions about that so far? Okay. Of things that you can cluster. And it should just, well, okay, it takes a while to build up. Yeah, a lot of stuff, basically. So clustering is not a bad first guess if you get some new data. You know, you might just check, you know, are there, you know, sets of observations that are much more similar to each other than they should be just by random. So for instance, for spammers, maybe, you know, there's one spammer who really sends out a specific set of spam. You've probably heard about the 419 scam, right? It's basically the Nigerian spam, right? This will cluster very nicely. So if you think about all the spam that you're receiving, you can very easily categorize it into certain subtypes. So in other words, if I'm able to do clustering on my emails, and I identify, this looks very much like a spam email, this allows me much more efficiently to detect spam. Likewise, location. So for instance, well, this place here would most likely be a geographic clustering location in terms of where people go. More to the point, the lecture theaters would be places that have a very high aggregation density. So here's the simple thing, namely a mixture of Gaussians. It's probably about, by now, 50, 60 years old at least. Actually older than that, it's I think 100 years ago, this was used to model the distribution over different crabs in Naples. So some fishermen measured like 1,000 different crabs in size and weight and God knows whatever. And then essentially it was discovered that it's actually not just one specific kind of crab, but they're basically 3 different subspecies. And they found out about that by basically clustering the sizes and weights. Because other than that, they looked very similar. And so the idea is basically you draw the cluster label from the discrete distribution, you draw the data from a Gaussian, and then if we have a discrete distribution, a good prior would be a Dirichlet. So that's like the Laplace smoothing that you would use for words. And for the Gaussians, it's the Gauss-Richard that we already did before, where you add something, to the mean, you add something to the variance, everything's good. The trouble is, we don't really know why. So in other words, we don't really know which cluster each data point belongs to. So if I told you what y is, everything would be really easy, right? Because then it's just a standard, maximum likelihood Gaussian or maximum posteriori, fitting Gaussians to the various clusters. So in other words, if I told you that this point here, for instance, was drawn from cluster 2, well, that's easy. Then I just take all the points that go into cluster 2, and I, estimate my mean mu2 and my covariance sigma 2. And I do that for here, mu1, sigma 1, and I keep on doing this. And once I have it, I'm done. And this, in a way, is the basic idea for k-means. It makes a couple of other crude assumptions, namely, it assumes that all the covariances here are the same. So we're not really fixing them. The only other thing is that then, boils down to finding the centers of the Gaussians. So one thing that you could do if you didn't know what the y's are, is you could just say, well, let's assign it to the cluster center that they are closest to. Right? And once you've done this, you can update what the mean of that cluster center is. So the first step is this green step over there. Find the closest cluster center. Then, once you have that, update the mean. Once you have the means, you update the cluster centers. Well, you update the assignments again, and you keep on iterating. And, well, this will at some point get stuck. And that's it. And this is why k-means is not doing such an absolutely horrific job at clustering. So it's like an idiot-proof simple algorithm. You can easily implement it, for instance, using MapReduce. And the problem is it doesn't really do much in terms of probabilistic representation. You can get stuck in local minima, so a lot of horrible things can happen to you. But it's simple. And if you do that, you see what happens. So initially, pick some random cluster centers. You then assign the points. You then update. So basically, your cluster centers get updated slightly, and you get the new partitioning, and you keep on doing this. Okay. Any questions about the basic idea so far? Good. So now we're going to get to something that many of you might have heard of and might have been scared of, but it's actually a lot less scary than you think. This is the main reason why we covered information theory. Because, at least, the main reason why we covered information theory for the purpose of this class. I mean, information theory in its own right is really useful, but okay. Expectation maximization. Who's used the EM algorithm at some point in the past? Cool, that's great. So the EM algorithm, intuitively it's like, well, here's some variable I don't know. Let's find a good estimate of the distribution over this variable. Let's use that as a guess to find a better estimate for the parameters, and then update my guess for the variables. So that sounds very much like k-means, right? Except that in k-means we made this hard assignment, and here in EM we just do a soft assignment. Now, that sounds very intuitive. Now let's try understanding the math behind it. So let's say we want to do a maximum a posteriori or a maximum likelihood fit over the cluster probabilities theta, the means and covariances for our Gaussians. So we need to maximize with respect to theta, sigma, and mu, p of x given all those parameters. Okay. So that, looks really easy, right? I mean, all you have to do is you just sum over, the unknown cluster assignment. So you sum over all the y's, and obviously I could even go and swap those sums. In other words, I could get something of this form. Product I going from 1 to m, sum over yi, p of xi given yi, sigma and mu. So these are actually entire, sets of sigmas and mu's, because only once I know yi, I know which one to pick, times p of yi given theta. So swapping the sum and the product is straightforward because it factorizes. But this is a nasty problem to solve. So here's the general idea behind EM and a lot of other non-convex minimization problems. And if you understand that basic idea, you can derive EM, and there are at least 3 different, almost schools of, deriving papers which work on the same algorithm and call it differently. It's called also DC programming, as in difference of convex functions programming. It's called the M method, and it's also called the concave convex procedure. Okay. The fact that there are 4 communities which are more or less independently publishing this stuff suggests it's a really important algorithm and fairly fundamental. Okay. So let's say I have some function that I want to minimize, and it's ugly, right? So it has a couple of local minima, right? And I want to minimize the blue function. And I know that, minimizing a convex function is fairly straightforward. I can do that. At least let's assume that I have an efficient convex solver. So how can I turn this nasty stuff into something for which I have a subroutine that is efficient, invoke that subroutine several times? First thing to note is obviously there is no guarantee that this will give me optimality. Because I have a general non-convex function, I might be just looking all over here, but maybe there's a really nice minimum over there, and I will just not find it. And for many algorithms, you don't have much of a guarantee in terms of finding global minimum. Okay. So what's an easy way of solving this thing? Well, the easy thing is you go and compute a convex upper bound on the function that you want to minimize. You then minimize that convex upper bound, you get a new value. You evaluate this function again, you get the new convex upper bound, and you keep on doing this until at some point you're stuck. And that's what EM does. So EM is going to give us a convex upper bound on the negative log likelihood of this mess up here. And this works for clustering, but it works for a lot of other problems too. And the various versions of what's called variational inference are essentially how brave and good with algebra you are to find a really good convex upper bound. And you can write lots of beautiful papers on finding tighter upper bounds. So if that's your kind of thing, you should do it. There are other simpler methods that require a lot less brains, namely sampling. I prefer those. But if you want to do variational, in some cases this is very efficient. Well, that's all you do. So now let's say we have this function here, and let's say I'm here and I compute the convex upper bound, right? So now if I minimize it, maybe I end up here. Let's say a new minimum. If I then evaluate the minimum of that convex upper bound, I get a smaller value yet again. So I'm basically winning in both steps. Okay, maybe didn't draw it very well, but suppose this were smaller than that. So I descend when I minimize the convex upper bound, and then I descend yet again when I evaluate the function. Now at this new place, I compute another convex upper bound, I descend, and then I descend again. So in both steps, in the minimization step and in the approximation step, I make progress. So of course the question is, how do I get this convex upper bound, right? And here's a very simple thing. Suppose I have a convex function plus a concave function. So this is convex. This is concave. So this is nice. And this one's a bit less fun. So if I have a concave function, I know that the Taylor approximation is going to be an upper bound on that concave function. It doesn't matter where I do this Taylor approximation, it's always going to be an upper bound. So now, the strategy is very simple. Take the ugly non-convex function, decompose it into a sum of a convex plus a concave function. Minimize the convex function plus the Taylor approximation of the concave part. Get the new function value, recompute, compute a new Taylor approximation, and keep on doing this. This, in a nutshell, is EM. Okay. Now, here's what we do in practice, right? So we now need to actually instantiate what it means to decompose my negative log likelihood into a convex and a concave part, then how to get that upper bound, and go through all the various details. This is the algebra right here. And Barnabas will have the pleasure of recapping that next Monday, because I won't be around. Question yet?
Can we approximate this function by some piecewise linear convex functions?
You could do that. So if I have this function here, I could make it a piecewise linear convex function, right? I could do this, right? But as you can see, this is a worse upper bound than just a straight line. So you're just making your life harder in terms of solving that new problem. And on top of that, the bound is worse. So there is no benefit in approximating and upper bounding the concave function with a piecewise linear one that's convex. What you probably had in mind is that you would say, well, let's do this. And that's a great idea for other convex minimization problems, and this gives you what's called a bundle method. And so we don't unfortunately have time to go into detail here about optimization, but this gives you very simple, fast converging optimization procedures for convex minimization. So the intuition is great, but the application is different. For non-convex minimization, this is really what you want to use. Okay. So let me just walk you through the inequality such that you can think. I'm already, I think, 1 minute over time. No, sorry. Sorry, I still have 9 minutes. Okay, well, fine. Then.
Is this converted to a local minimum?
Correct. So this will give me a local minimum. So as we saw here, this is the minimum. This is where I really would want to go. That's what it gives me. Well, maybe if I'd initialized it somewhere over here, I would have gotten lucky, but, well, I didn't.
So it is definitely a local minimum.
It is okay, so you could, if everything went really poorly, converge to a saddle point. This could happen. But in practice you don't, because you have numerical error anyway, so this will take you out of the saddle point, albeit maybe slowly. So in practice, you'll get the local minimum. Yes. You're way too advanced in your question. So this is really just the basic simple parts. So what you might also do is use stochastic EM that will have a higher chance of getting you to a good local minimum and so on. So there's a lot of other tricks that you can use. But let's go through the variational bound. So, and this holds in general, and I've seen it derived over and over in many good papers for special cases, and that specific derivation was way more complicated. So this is the simplest derivation for EM that I know of. So the log of P of x parameterized by theta, so and I want to minimize that in some way, right? So for that, I need to find a lower bound. So because we afterwards want to minimize the negative log, so we get the upper bound. So for the log, we need the lower bound. Right? Okay. Well, this is nothing else but, it's obviously greater or equal than the log of P of x parameterized by theta minus the KL divergence between some distribution Q of y, and I can pick that as I want, and P of y given x and theta. So let's say, P of x parameterized by theta arose from integrating out or summing over the variables y. So this first inequality holds for any Q of y and any P of y given x and theta. Right? And we know that the KL divergence is greater or equal than 0. So now let's plug in terms. So that's the integral dq of y of log of P of x parameterized by theta. Since it doesn't depend on y, I can just pull it into the integral, because the integral over a probability distribution is always 1. Okay. Then I get the log of P of y given x and theta minus the log of Q of y. That's just how the KL divergence is defined. So there's absolutely nothing deep insightful from the first to the second line. Now, to go from the second to the third line, the only thing that you need to use is the fact that P of x given theta times P of y given x and theta is P of x and y given theta. So the y's might be, for instance, your cluster memberships, right? Okay. And then the other thing that I'm going to do is I'm going to split up the integral. So now we have a term that depends on theta, and we have another term that doesn't depend on theta. So now if I want to maximize this, I can go and maximize the first term. And then afterwards, after I'm done maximizing the first term, I can go and find a better Q. Now since this is the KL divergence, finding a good Q is easy, right? Because we know that the KL divergence vanishes exactly when Q and P of y given x are the same. That's why we needed information theory for that one slide. Okay. Now, this is all we have. So the E step is finding Q of y equals P of y given x and theta. This finds a new bound. And then the maximization step is maximizing the expected log likelihood of P of x and y given theta. This is it. So if you ever are asked to, use EM, remember that simple derivation and you're home. If you understand this, you understand all of variational calculus in machine learning. There are a lot of techniques and tricks on how you construct your Q efficiently and how to get those quantities, but this is it. There's nothing else to it. Well, okay, the slight thing is that in some cases finding that bound isn't so easy, and then you approximate and so on, but in terms of concepts, this is all that there is to it. Any questions so far? Because you need to understand that slide to understand the application to clustering. Okay. Good. No question? Okay, thanks.
It's like the end step is very hard.
Correct. So the maximization step is really unpleasant in some cases. Now, what you do in those cases is that you cheat. Rather than finding a Q that really lets the KL divergence vanish, I pick some Q that, well, we have another 3 minutes. Maybe you can turn the alarm off. Thank you. So basically what you do is you cheat. You cheat insofar as you basically find a Q for which this integral is, tractable to compute. And tractability is very much a function of how smart you are and how fast your computer is. And that's where you write the papers. And then, rather than finding a Q, you find a Q that is close enough that basically minimizes the KL divergence to the best of your abilities. And then, of course, this is not quite exactly a proper variational method anymore, because we are not really, we're never really close in that bound. So this is sometimes called structured mean field, or it's called structured EM. So the difference is that, well, remember here we had a tight approximation. Now in this case, well, we just get some upper bound. There may be a gap here. And this is what comes from dealing with our potential inability to solve that integral, so we have to cheat with Q. This would be something to be discussed in, let's say, Eric Singh's class on graphical models. But that's just useful to know. Now let's actually look at it for clustering, and then we can conclude. So the good thing is that for clustering EM, this doesn't happen. We're in that scenario here. So let's just pick some factorizing distribution. Q of y is product over Qi of y. And that's okay, because I can actually work out P of yi given xi, mu, and sigma. Right? I can do that because, well, I've just constructed my graphical model this way. Remember, we had the y's, we had the x's, and here we had some parameters, mu, sigma, here we have some theta. And here we have the plate. So in this case, we have the fact that those y's nicely factorized, and so I just can work out by base rule that this is proportional to P of xi given yi times P of yi. So in other words, I just check how well does a particular cluster fit that particular observation. And you get that here. And so then I just renormalize and I get the Qi's. And at that point, all I have to do is compute the expectation of the log likelihood with regard to those yi's. So I basically take the average over, the contributions of the data to a particular cluster. And now, essentially, a single observation may get split up over more than one cluster. So let's say, for instance, I have as a probability that this belongs with 20% probability. I think it might be in one cluster and with 80% in another one. Then the corresponding observation adds to the statistic for one cluster with 20% and to the other cluster with 80%. That's what we have here. So that's why we now have, the means and the covariances being weighted versions. That's what I have here. So ny is the effective cluster size. And this lets me, just as I would, update the means and the covariances, and then I repeat the previous step again. So I basically alternate between this and that. And this is what you get in practice. After a few steps, you get something that's quite nice. Sort of, kind of. So the problem is that this will diverge, and for this is exactly what you use smoothers. So Barnabas will pick up with that next week. So I'm not around next week, so there are no office hours for me next week. And I'll be back the week thereafter. Okay. Any questions? Okay, sorry, this was a tough lecture today. Maybe if somebody could press the stop button on the camera, that would be great.